This is a video solution of our study guide, and what I'm going to do is I'm just gonna skip over some stuff that you can find in the book or some stuff that might not be covered on the test, and just focus on the things that you should really be preparing for. Alright, this first one's fundamental theorem of calculus. The first question is asking us to state it, so this is one of those ones that I will skip because you can just see the book, and the book has that information. Alright, let's go to the second one. This second one's a little bit more challenging. Suppose an antiderivative is given by this function, and we don't know what little f is, and they want us to find the integral from 0 to pi over 4 of little f dx. Well, we know by one of the fundamental theorem of calculus, part 2 I believe, is that the integral of a derivative is equal to the original function, or since this is the function, it's actually equal to the antiderivative evaluated at the top limit minus the antiderivative evaluated at the bottom limit. Now fortunately they gave us what the antiderivative is, so all we have to do is use that function and put in a pi over 4 wherever we see an x, and then subtract, and then put in a 0 because that's our lower limit. And tangent of 0 is 0. Well, if you didn't know that, you'll probably just leave that here, but sine and tangent of 0 are both equal to 0, and a cosine of 0 is equal to 1. So this is a tangent. It goes to 0, everything goes to 0 over there. We have the square root of e to the pi over 4, and it turns out that tangent of pi over 4 is equal to 1. So we could be done there. Let's just make a note that this is equal to 1, and this is equal to 0. So this is our final answer. Okay. The second one is asking us to find the derivative of f, where f is defined as an integral function. Now this integral function is already set up for us where x is in the top limit and we have a constant in the bottom limit. The other part about this is that we didn't really talk about the sinh function, so I don't know, you probably wouldn't be expected to find the integral or the antiderivative of that, and finding the antiderivative of square root of t to the fourth plus 1 is very complicated. So you should expect to use a formula for this, and we know that if we are taking the derivative of this thing, then it's simply, remember this is a t, the dummy variable, and you plug in the x, so it's the derivative of the integral of a function is the original function evaluated at the limits, or in this case at the top limit. So let's just say sine hyperbolic x squared minus the square root of x to the fourth plus 1. So this is your answer for that. And it was just a matter of remembering our new derivative formula. Question number 2 is asking us to find the area under the curve. So for this one, what we want to do is for all these problems, it looks like we're dealing with an interval between 0 and 1, and n is going to be equal to 4 both times, so that's nice for us because we can just find these points over here, and then we have labels and we have the actual partition. So your partition is 0, 1/4, 1/2, 3/4, and 1. where this is usually referred to as x sub 0, and this is x sub 4, and then you have x sub 1, x sub 2, x sub 3 in between. Alright, now we want to estimate this using the left endpoint. So for the first subinterval between 0 and 0 and 1/4, the left interval is 0, and then and so on. So I guess first thing we should do is we should figure out what our delta x is. Delta x is that we have an interval going from 0 to 1, and then we have 4 of them, and so our subintervals would be 1/4, and we can kind of see that each of these lengths of the subintervals 1/4. So now that we know that it's 1/4, let's write out the. You should probably know the formula for this, but I'll write it out using base times height. So the base is delta x, and the height for the first rectangle is going to have a height of, using the left endpoint, is 0, but it's 0 into the function. So this is our function over here. Plus the second rectangle is going to be base times height again. The base is going to be the same, so we'll see next time we'll do this a little bit quicker and factor things out instead. So this is the left endpoint. This is LH for left hand. So for our second interval using the left endpoint, we're going to choose 1/4 to put into our function, and then the third interval between 1/2 and 3/4, we're going to choose to plug in 1/2, and then the last interval we're going to choose to put in between 3/4 and 1, we're going to choose to put in 3/4. Now, as you can probably notice, so we can factor out a delta x. We have e to the negative 0, or let's just say 0, which is equal to 1, plus we have e to the negative 1. I guess this is 4 squared, so that's 16, plus e to the negative 1/4, plus e to the negative 3/4. Let's call it 9/4. And then multiply everything by 1/4. That's delta x that we factored out. So this one we can punch into the calculator. We'll do that a little bit later. For the right hand rule, or the right endpoint, we'll see that it's basically the same, and we can try to get a pattern out of this. We have e to the, we'll start with the right hand, which is negative 1/4. That turns out to be this business over here, negative 1/16. And then we move on to the second rectangle, to the third rectangle, and for the fourth rectangle, the right hand rule will get us to choose 1, so e to the negative 1 squared, and then the delta x was factored out, so this is all set to go here. We want to estimate our area using the midpoint. Let's use a different color for that. And so the midpoint, essentially you have to find more points here now for each of these subintervals, so we can figure this out. This is an eighth, this is 3/8, 5/8, and 7/8. If you want to count by eighths, is 1/8, 2/8, which is 1/4, 3/8, 4/8, which is a half, etc. So for each of these subintervals, you're just going to put in the eighths. So this is 1/8 squared plus e to the negative The next one is 3/8, and then e to the negative 5/8 squared, and then the last one e to the negative 7/8 squared. So multiply that one by 1/4 and you would be done. So let's take out our calculator. And my y1 is already set up. So I'm going to go my stat and enter for edit. Now I have L1. So for L1, for this first one, I want to put the numbers 0, 1/4, 1/2, 3/4, and then those are going to be my left endpoints for my 4 rectangles. So what I can do is I can just put all that information in here, but let's actually use a sum function. Actually, while we're at it, we might as well fill in the rest of these values for L2. This is going to be for my right hand. And for my right hand, I'm going to put 1/4 for my first one, 1/2, 3/4, and then 1. And then for my midpoint, I'm going to put 1/8, 3/8, 5/8, and 7/8. Alright, so I'm going to go back to my home screen by hitting second function in mode. That would quit me out of that. And let's clear whatever we have there. Now the sum is a function that you can get from list. So the second function in stat would open up list. If you go to the third one, math, and the fifth one down is sum. So we'll select that. So look at what we're adding up. We're adding up a sum of the function evaluated at those values. So the function was, remember, in y1. So to access y1, we're going to press second and vars. We're going to, let's try that again. Second, nope, not second, I'm sorry, just vars. So you hit vars and you go to y vars and you'll select 1 or just press enter for function, and there's y1 right there. So that's y1, and for each value in y1, I'm going to open parentheses and click on second and the number 1. For each value of x that I have in my list L1, I want to put that into the y1. I'll close this, and then for each of them I want to multiply by 1/4. So let's say times, and then just because we're dealing with fractions, I just want to be safe and put parentheses around 1/4. Close the parentheses, and we can close the sum function as well. And we'll press enter. So it looks like our value for this is 821.9 or 822. So let's make a note of that. Now let's take a look at our right hand rule. And for a little trick for your TI-83 or 84, if you have that function already up there and you want to change one little minor thing, like I just want to change my L1 to L2, I'm going to go back to second function and enter. That's going to give me my last entry, and I'm going to just use my arrow keys to I can delete this and insert, or I can just overwrite it right here. Let's go back to L1, second function number 2. Now it's L2, and if I look down here, it's pretty much the same except it says L2. Let's press enter. We should get something significantly higher because this would be an overestimate, I believe. Oh, significantly lower, sorry. That would be 0.6639. Let's just say 0.664. So one's an overestimate, one's an underestimate, and if we explored this a little bit more by looking at the shape of the graph, we could probably get a closer idea of whether we should be expecting over and under estimates. But usually midpoints are better at estimating, usually, not always. So I have my midpoint values in L3, so I'm just going to recall that last command and go to my L2 and replace that with L3. And then I get 0.748 or 0.749. And then for this last bit, they want us to actually use our calculator, find exact area, and we have our value in my function y1 already. So let's click on second function in calc, and if you look down here, one of the options in number 7 is fx, or the integral. So I didn't graph it yet, so maybe I should think about graphing it first. Let's clear this, because I don't think I have appropriate windows. I just want to go from 0 to 1, and I don't know exactly how high this is going to go, so let's do a standard plot first. So let's do a zoom and zoom. Maybe we'll do a zoom fit. Well, let's do a zoom standard for now. I'm going to press 6, and then I'll plan to change the window. So the window is really small here. If I use a trace button, I see my highest value is 1, and I don't go below 0, it doesn't look like, so that's going to give me an idea of how to adjust my window. I'm going to go from 0 to 1 in my X. Actually, let's put a little padding there and change my window from -1 to 2. So let's say -1, 2, and then X scales of the 1 would be good. Now my Y min, I can put 0 here, but I'm going to give it a little leeway and put -1 again. And then I know my max is going to be at 1, but I'm going to again give it some leeway and put 2. Alright, so we can graph it first, and then we can actually do the integral. So this is the piece that we want, so let's compute the integral. Second function in trace, and select number 7, or wherever you have your integral. It's asking for the lower limit, so I'll just press 0 for my lower limit, enter, and my upper limit is 1, enter. And then here they actually shade it for us as well, so that's nice. Well, let's copy it and paste it onto our notes. So now we have this integral, and let's actually label it appropriately. This here is the integral from, I guess the only difference here is we'll add the limits from 0 to 1 of e to the negative x squared dx is approximately equal to 0.7468, and so we came really close with our midpoint. So that's problem number 2. So this one takes this 3 steps to use the definition of the definite integral to have us compute this definite integral. And this is kind of equivalent to using the definition of the derivative to compute your derivative, where the shortcut would be a lot easier. In this case, this work over here is pretty time consuming, and it's not going to be on your exam, so I'll just skip over it. We do need to know some integrals, and we do need to be able to use the fundamental theorem of calculus. So we will use the fundamental theorem of calculus just to do a simple integral here, and just as an exercise. So this one, we can separate this into 2 integrals, or we can just go ahead and integrate piece by piece since we know that's a valid rule. So the antiderivative of 4 is going to be 4x. Antiderivative of x squared is going to be x cubed over 3. and then we want to evaluate this for x values between 0 and 2. So if we put a 2 in, we're going to get 4 times 2, and then 2 cubed over 3 minus, and then you put 0 in, but 0 is just going to have a 0 contribution, so that's not going to be anything. Here we have 8 and then 8/3. So if we have a common denominator, that would be 24, and 24 minus 8 is going to give us 16. So this should be our final answer. So that's problem number 3. Problem number 4 uses a function and its graph to help us compute some values. So given the graph above, they want us to find the following. So this is the graph of v. They want us to find the graph or the integral from 0 to 6 of v of t. So to find that, what we want to do is we want to go from 0 to 6 and try to see if we can compute some areas here. So I think an important thing for us to do is figure out some areas. And I'm just going to partition this into pieces of geometry that I know the areas of. This is going to be a 1 by 1 square. So I know that these will have values of 1s and these will have values of 1/2. And the other thing that's important to note is that with these values that are below the x-axis, we're going to be given a negative contribution. Alright, so if we take a look at this negative contribution here and positive contribution of 1, so we essentially have 3 here, and then negative 3, and then we have a positive 1. So when we put all that together, it's going to be a negative 2. So that should be the integral here for our value. And this is all geometry. And our geometry is looking for areas of circles or areas of triangles and rectangles. And in a test situation, you may be asked to find the area of a circle. Okay, so that's our first one. Let's do the second one. The integral from 2 to 4 of v of t dt. So this time I'm just going to go from 2 to 4. So this is all negative contribution, and that looks like it's going to be 1.5 or 3/2. The next one from 6 to 4. Integral from 6 to 4 v of t dt. Now this is a little tricky because we have the lower limit is larger than the upper limit, so what we might want to do is we want to switch that around, and when we switch our limits around, we have to throw a negative sign in front of that. That's one of the rules that we learned. And now we're looking for the integral from 4 to 6. So 4 to 6 gives a positive 1. But then there's a negative sign in front. Oops, now it looks like an equal. Here we go. Negative sign in front. And so that has to be negative over here. So it looks like our answer is going to be negative 1. And then finally, we take the integral from 3 to 5 of v of t dt. 3 to 5. It looks like in this particular case they cancel each other out. We have a negative 1/2 contribution from 3 to 4 and a positive 1/2 this contribution. So we can write those areas down, or we can just simply write 0 because that's what the answer is. Alright, now it's saying for this part B, S is an antiderivative of V, complete the table. So in this particular scenario, when t is equal to 0, we're starting off with an antiderivative t is equal to, imagine an integral of v of t dt is going to be, the indefinite integral is going to be any antiderivative plus a constant. So maybe the c represents that constant for this particular antiderivative. So from here, we just need to take into account the contributions that our area is going to make as we move along from 0 to 6. So here we start with a 2 and we subtract out a 1/2. So 2 minus a half is 3/2. And then as we move along, we subtract off another half over here. So this is going to be 1/2. And by the time you get to 3, you subtracted out another half. So we are left where we left off at 1/2. And then we need to subtract off another 1/2. So this is going to be negative 1/2. And now we got another 1/2 contribution over here in the negative direction. So negative 1/2 minus 1/2 is going to be negative 1. And then up here, we pop up. So we get negative 1 up to 4, and then to go to 5, we add a 1/2. So negative 1 plus 1/2 is again negative 1/2. And then from 5 to 6, we add another 1/2 factor, and that brings us to 0. So this should be our complete table that uses v, the graph of v, as a function, and then s is the given antiderivative with an initial value of 2. So once you know that and you know how to calculate the areas, then we can use the graphic representation to fill out a numeric representation for our function or for our antiderivative. Okay, so that's problem number 4.